Check it out. Okay. Matt, you all ready? I'll queue it up in a sec. Oh, okay. We're not streaming till 9:15. Okay, cool. start the live stream, please.
Don't forget to thank the funders. Yes, I know. I'm sorry. I forgot yesterday. I realized that.
Just going to wait till it quiets down over. For the noise level down a little bit, and we'll get started as soon as we can. Thank you. Okay, thank you very much. Good. Yeah, do you have a pen? Thanks. That's okay. Thank you. Okay, thanks. Okay, so thanks very much. We're going to get started. Thanks to the generosity of the Russell Sage Foundation and the Alfred P. Sloan Foundation, I'm very pleased to talk to you today about collecting digital trace data. We're coming to you here from Duke University, and hello to everyone following along on our live stream around the world. So we're going to begin with some general discussion of what digital trace data is. We're then going to move into a discussion of its strengths and weaknesses. And the lecture today will be very similar to yesterday's lecture if you tuned in for our lecture on ethics, which is to say it's going to be kind of very broad in scope. And then we're going to get into the nitty-gritty. So once we get into the mid to late morning, we'll be working through code together to learn how to do things like screen scraping, browser automation, and by the end of the morning, we'll be laying out the groundwork to help you understand how to build apps and bots for social science research. So let's begin. Here's our schedule here. And sorry, I wanted to also point out, tune in today at 4 for a great guest lecture by Jim Wilson, who's a program officer at the Russell Sage Foundation and former professor who's going to talk to us about getting grants, particularly in this area, but also just kind of more broadly the grant-making process, something that many of us need to learn more about. Okay, so what is digital trace data? Well, yesterday we had a fantastic lecture from Duncan Watts, and Duncan, as his research presentation showed, was a pioneer in this area. And Duncan likes to describe digital trace data as kind of our telescope. So I like this quote from a recent book he wrote. Actually, it's not so recent anymore. Just as the invention of the telescope revolutionized the study of the heavens, so too, by rendering the unmeasurable measurable, the technological revolution in mobile, web, and internet communications has the potential to revolutionize our understanding of ourselves and how we interact. 300 years after Alexander Pope argued that the proper study of mankind should lie not in the heavens, but in ourselves, we have finally found our telescope. Let the revolution begin. Okay, so exciting. To have a reckoning with these data. Yesterday, Matt talked quite a bit about the hype cycle in the field of computational social science. And I think, whereas when Duncan was writing this in 2011, we really were looking at this as many people were even thinking it might be a replacement for some more traditional forms of data. And a kind of persistent theme that will come up today is that these data probably in and of themselves aren't going to solve most of our most pressing theoretical concerns. But when combined with other sources of data, like survey data, in the form of, say, an app, we can really reach that plateau of productivity that Matt was talking about yesterday. So let's talk about some examples of digital trace data. Perhaps the most obvious one is social media sites, Facebook, Twitter, Instagram, whatever the kids are using today. Web search data, right? These digital traces of human behavior that we leave all over the internet. Some people still blog, I guess. So blogs, other internet forums, and also importantly, non-internet data. And I think too often when we talk about digital trace data, we tend to focus only on the social media data, when really one of the most exciting developments is that we've begun to time travel. Things like administrative data on websites and the large-scale digitization of historical archives, such as, of course, the Google Ngrams corpus, but there's many other examples that are really just screaming out for analysis by social scientists. And so when we think about digital trace data, we can really look at a lot of different places. And tomorrow, when we talk about text analysis, we'll talk about how to turn these unstructured data into clean, square data frames that we can analyze. But today, we're going to focus mostly on just getting these data. So an example of these data, this is a nice visual that was produced by Michael Macy and collaborators, where this paper, which was published in Science many years ago, visualizes the network of cell phones in Britain. And these kind of early, this is a very popular map produced by a Facebook data scientist some years ago. Shows that it created tremendous enthusiasm that if we could map the world with these data, what couldn't we do, right? And then the urinal, right? So this is Matt's. This is the great example from Matt's book, Bit by Bit, right? About the kind of ready-made versus custom-made data. So if we're thinking about digital trace data, right? It's something that was not produced for social science research. It was something that was produced for people to communicate with each other very often, or for advertisers to sell things, or some combination of the two. And so just as Duchamp's urinal here was transformed into a work of abstract art, the task of the researcher working with digital trace data is to figure out how to repurpose these data for analyses that it was never intended. So we're not doing the Michelangelo, right? We're not building the study up from the ground, defining exactly what we want to ask who and when, where, and why. More often, we are kind of peering in with our telescope and saying, what is this, first of all, right? And then, can we use it? Can it be reasonably repurposed to measure and evaluate and understand a social process? And that's going to be the great challenge we face today. And I like this Picasso analogy better. Sorry, joke. I don't like the urinal. Okay. Okay, so now we're going to transition a little bit. If you're following along online, you will, we're just going to come back to the Summer Institute homepage, and we're going to transition to the second part of the lecture, and that is the discussion of strengths and weaknesses of digital trace data. So if you're following along, we are on Tuesday, and you can follow along with my slides right here. Okay. So what are the strengths? Let's start with the good stuff. So yesterday, Matt began to mention some of this stuff, right? A huge strength is that digital trace data is very large, right? So here we have this graph of information storage. This is only taking us up to 2007. But in 2012, the amount of information collected, the amount of data collected in 2011 alone was the same as all data collected in all previous years of human history combined. And I think the last data points I've read on this suggest we're surpassing that even more rapidly each month. So that's exciting. Now, to put some cool water on that, much of that is, say, pixel data, data that's not necessarily measuring important social processes. But I think we could all agree that thanks to the increasing size of data and increases in computing power, which have allowed us to both collect it and analyze it, we're in a much better position as social scientists to look at large-scale processes. And in some of Duncan's earlier work, he signaled one of the most promising potentials of this work was that we could maybe look at population-level processes, right? That we are typically in the business of taking a random sample from a population and trying to understand the population. And that if we really do have data about a whole social space, and that whole is key, right? It's not everything. So we might have a population of Twitter users, and as we'll see as we get more into the data today, this is emphatically not representative of many or even most offline groups, right? But if our goal is to generalize to that online community, then we have a population level sample in many cases, which is really exciting. Second, these data are always on. So, very often as social scientists, we're in the business of making a survey, and we have to predefine what we want to measure. So we have to know what kind of questions we want to ask, what kind of people to answer a question, right? And a huge virtue of digital trace data is that they're always being collected, they're always on. And as a result, we can very often work backwards and collect data on the kind of more stochastic elements of life, right? Things like the Tahrir Square protests pictured here, right? Where we're able to kind of go back and have data points. Now, what those data points mean is going to be, again, a very important thing we need to think about. But we can recognize the stochastic nature of so many social processes and capture these, particularly these unexpected or even unprecedented events, such as the Arab Spring. Third, digital trace data are non-reactive. So very often when we're collecting, say, a conventional survey, we worry about things like social desirability bias. So for example, if we want to measure here self-induced abortion, and we were to do a study of self-induced abortion, right? The survey we might worry would have a significant amount of social desirability bias, right? Nobody wants to discuss that issue before a survey researcher who they have no previous experience with it, right? Or similarly, in other work, I've used Google search data, which is pictured here. These are searches for self-induced abortion in the US to track things like violent radicalization. So people who might become violent radicals might Google something like how to join ISIS, right? Not very intelligent people, of course, but these people would be unlikely to announce themselves as violent radicals before a survey researcher, right? So another huge advantage of digital trace data is that they're kind of naturally occurring, right? They don't result from the intervention of a researcher. right? And that's kind of a bug and a feature, because if we were making Michelangelo, right, if we were building up a study from the ground up, we like to be able to define all the parameters. We like to be able to define all our questions clearly. But when we do that, right, we have to engage subjects, human subjects, and that creates, in many cases, a serious amount of bias. Okay. This is another important one, captures social relationships. So, we very often, many of our theories, especially those of us who are interested in social networks, right, we often want to test theories about social relationships, not about individual attributes, but about how people are connected to each other. And if we do this in the context of a traditional survey, right, if we want to build the network of the people in this room, we'd have to administer a survey to everyone, ask them to describe everyone they know, right? And this would be a very, very greedy or very time-consuming process, right? We would have to ask a lot of people a lot of questions. And even then, we'd face some important problems that a social network or a researcher might call the boundary problem, right? So where do we stop doing that sampling process, right? All of you are probably connected to people outside this room and share kind of a second-degree connection with each other. That would be really tough to pick up. We'd have to interview untold numbers of people to really map the whole population. Again, in these online settings that we may be interested in studying, so here is the European Parliament members' Twitter networks, exciting group of people that they are. That got a laugh from the Europeans. We can actually start to see clusters of social relationships. And that has immense value in a field where so many of us are interested in the science of social relationships. How our relationships to each other are predictive of things like the spread of information, the spread of disease, who gets a good job, you name it, right? So the strengths are big data are big, non-reactive, they capture social relationships, and they're always on, right? And those are big strengths, right? We don't want to forget that there's a lot of good that can be done from these types of data alone, but they have so many weaknesses. And I think, early on in the field of computational social science, this was not yet well known. We still had many people kind of celebrating and touting the strengths of big data, right? As Matt mentioned yesterday, we had people saying, we no longer need theory, right? Because we have data now, right? And now many of us, can look back on that as something extremely silly to say, right? If anything, we need more theory. And so we can imagine many of the weaknesses. Bit by bit, Matt's book has a good discussion of this, and I'll draw from that and add a few of my own. So first, it's just that these data are incomplete, right? So earlier I mentioned that big data are always on, that they are non-reactive, but let's say we wanted to do a study of, say, harassment in some kind of online setting, right? We would soon discover, right, hopefully, that many comments that we might be interested in measuring as a key outcome in our study of abusive behavior in some kind of online setting might be removed by the modifier, the moderator, right? And so big data are very often incomplete, right? This idea that big data is capturing everything, that it's always on and capturing everything. Now don't get me wrong, there are sources of data out there, such as Google takeout data. If we do the thought experiment, right? If Google has every Gmail we sent, every web search we ever made, every Google Maps step we ever took, every YouTube video we ever viewed, right? Which they do, right? That's an immense amount of information that in theory could be used to trace social processes with unprecedented detail. But of course, we can't access that data for good reasons, right? So big data are very often incomplete, even though we might want them to be representative. And much of the early work in our field kind of assumed that this data, again, we're going to somehow displace conventional survey data, right? Set expectations sky high, right? That if the data didn't answer all the world's questions, then they were junk, right? And so now we're running into situations like this. We're realizing that big data can be very incomplete. And as I just mentioned, big data are very often inaccessible. So, a good example is Facebook, right? Many of us have research questions that could be very interesting to examine with Facebook data. And though, large chunks of Facebook are in the public domain, Facebook fan pages, and so on, the vast majority of Facebook is off limits to us researchers unless we obtain permission to access data from users or collaborate with industry, right? And this goes for, of course, sites vary, right? Twitter is fairly open. It's perhaps why it's become such a locus of research in our field, because it's fairly straightforward to get Twitter data. But on the other hand, other sites such as the aforementioned Google Takeout data, right, which is all that Google data packaged together, right? Just like as you download your Facebook account, you can see all of the information you've ever produced. You can do the same with Google. And we heard last year from a researcher who built a pipeline to analyze Google Takeout data in a very creative manner that allowed them to kind of analyze these data without ever downloading them onto their servers. That was work by Deborah Estrin. You can check that out on the archive videos from last year if you're interested. Okay, so they are not accessible. They're also not representative, right? And this kind of dovetails with the incomplete issue as well, right? So we can see here, these are just some simple racial demographics. This is from an older Pew study. This has changed a little bit. But if we're looking at the national or US population, and by the way, these figures vary tremendously across countries. If we were looking at Turkey, for example, Twitter has extraordinarily good coverage in Turkey. But if we're looking at the US, parochial as we may be, we can see even in our own top 3 or 4 social media sites, pretty significant, in this case, racial and ethnic differences in who's using which platform. And so if we go through and say, want to make claims about attitudes about race using Twitter data, right? Or if we want to really pick your topic, right? That has that's influenced to some degree by one's racial and ethnic identity, right? We have huge issues around our sample, right? We can't take Twitter data as representative of the entire public if it has a larger share of the, for example, the Black and non-Hispanic population than other platforms. Now we can there's some new promising directions, some of which Matt will talk about on Thursday, I think, such as post-estimation weighting, where we can start to try to tease out some of these things. But anyone who's just going to try to do a study that is inattentive to the non-representativeness of social media data, right, is going to get into serious trouble with reviewers or anyone else who's now familiar with these type of dynamics. MySpace. This is where I show my age. Who was on MySpace? Matt, okay. But there's it gets worse every year. Okay, so MySpace, for those of you who don't know, was kind of the original social media site. It was really the thing for, I don't know, a year there, maybe a year. Okay, so, and now nobody's heard about it, right? And so this is an example of what Matt, I think, nicely calls drift, right? That, all the time, all of these platforms are changing, right? If we're talking about digital trace data collected online, right? So the other joke I like to use with my undergrads is I say, well, how many of you are on Facebook? And they all raise their hand. And then I say, well, how many of you are on Instagram? And then they all raise their hand. And then I say, well, which one do you use more? And they say, well, Instagram, blah, blah. And I say, okay, well, why don't you use Facebook? And they say, well, because our parents are on Facebook, right? So there's these different groups of people are drifting on and off the platform. The platform itself is also changing over time, right? So they're becoming more widely used by different types of people, more or less widely used. And so in the case of MySpace, an early study of MySpace that then, say, wanted to generalize to some future social media site has this obvious issue, right? That the platforms are always changing. And today, just to add an aside, we have an additional, perhaps even more daunting problem, which came up in some of the discussion of Duncan's work last night, which is that things are spreading across platforms all the time, right? And there's very little research on cross-platform spread in the exchange of even just simple things, relatively simple things like the spread of information across platforms. Algorithmic confounding. This is a plot from a paper by David Lazar, Gary King, and some other co-authors. David Lazar will be visiting us tomorrow night and giving a speech. And this is a really nice paper. It takes the Google Flu data. Google Flu was a tool that was developed by Google Labs some years ago. And what happened is Google data scientists recognized that they could track the spread of influenza very well with Google search data, or so they thought, right? And so what we see up here in this top panel is in the orange is the Google Flu estimate of the prevalence of influenza over time for about 2 years. And then in this blue line here is the estimate from the Centers for Disease Control, which is the body of the US government responsible for tracking disease, right? And then we have some lags in here too. And what we see is for 2 years, there's really great tracking. Google Flu is really just nailing it. And then one day or 1 month in late 2012, the Google Flu estimates started outpacing the CDC estimates by more than double, right? And so this caused great concern, right? Is there a major influenza outbreak that we've all been worried about for many years? Or was there something wrong with the data? And so in this paper, Lazar et al. Kind of go through and try to do a postmortem or a diagnosis of what happened and discovered that this increase was likely the result of what they call blue team dynamics, or the tendency for some property of the social media platform to change users' interaction with the platform, which then becomes interpreted as some kind of meaningful signal about social behavior, right? So in this case, people who were searching for symptoms of the common cold then saw an ad about, say, the flu, and then started Googling things about the flu. And so these are very, very major problems, and there are, one of the most daunting things about this problem is much of the information about algorithmic confounding is not in the public domain. Just a few more. Big data, digital trace data, they're messy. Again, I think people like to think of digital data as being inherently clean, but especially because so much of the data we're working with is text data, right? It's unstructured. It's not the neat zeros and ones we might like to see in a CSV file to run our models on, right? And so we really have to do a lot of work data cleaning. In fact, a survey by the New York Times about 4 years ago of data scientists suggested that most of them spend about 80% of their time data cleaning and only about 10 to 20% of their time actually running models. And I'm seeing heads nod around the room. Many of you have had this experience. I certainly have, yeah. Sensitive, right? This is a huge one. Here, this was several years ago. A North European researcher caused an uproar by publishing data that he had scraped from some 70,000 OkCupid users, right? Now, we're going to talk about all the kind of reasons not to do this shortly when we talk about screen scraping. But it's worth noting because this wasn't even a case where there was some kind of accidental disclosure of information, which is another genre of sensitive data issue that we need to be very careful about, say one that was exemplified in the Cambridge Analytica case, but one that just simply resulted from some people compiling data that was available on the internet into one large database, and that merging, even of metadata, seemingly innocuous metadata, as Lazar shows in a new paper, can actually lead to identification of individuals. So we need to worry about that. Finally, there's some kind of a lead or publication bias in a lot of digital trace data, right? History is written by the victors, or just something like, people don't put everything out there about their lives on social media, right? And certainly there's positivity bias on something like Facebook, right? So here your Facebook posts make you seem really interesting, but remember, dear, there are people who know you in real life, right? Suggesting here that if we want to, again, understand, say, emotional dynamics by looking at Facebook, we're probably missing a lot of important negative emotions, and certainly emotions such as shame, right, if there is indeed this type of positivity bias. So the future, again, I think, we're all starting to agree. This is the hype cycle that Matt mentioned, the Gartner hype cycle from Monday's intro lecture, right? Digital trace data has been on this wild ride, right? We had this moment when we were really starting to say crazy things like we don't need surveys anymore, we don't need theory anymore, right? And then a set of very underwhelming papers came out, right? That said, now we understand the Arab Spring because we watched people tweet about it, right? Where were those people, right? Were they in Tahrir Square or were they in London tweeting about the event, right? We might be able to tease out some of that through some fancy techniques like geotagging, right? But were they writing in real time or were they responding to, say, the CNN message? And then if we're going to make these strong claims that Twitter discourse, say, caused a revolution, right? We have so many confounding factors, and then we didn't even touch on the representativeness issue, right? So really, these types of studies brought us into the trough of despair, right? And now today, and moving forward, we're going to try to get to the plateau of productivity. OK, any questions? We're about to get into the nitty-gritty of collecting digital trace data, but any questions or comments on what is digital trace data, strengths or weaknesses of digital trace data? Nothing, great, OK. All right. So if you just come with me then, I want to show you how to use the materials we're going to be working with. Because again, we're about to get much more hands-on. So if you come down with me here to the Tuesday, we are now right here at 9:45. We're about to start discussing screen scraping. The slides are going to be here. That's what you're going to see on the main screen. But I briefly want to introduce you to this annotated code link. And so if you come up here, you'll see that for each of the tutorials we'll be working through today and tomorrow, there are clickable interactive tutorials that include all of the code that you're going to see up on the screen. These are called code chunks. For those of you who don't know, this is a file format called Markdown. And this is a kind of worked tutorial that takes you through every single step. It includes the output of the code that we'll run and a lot of instructions about how to do each technique that we'll talk about, OK? So why do I mention this? I mention this primarily because I wanted to relieve you all of taking notes. If you want to follow along in real time, you're welcome to cut and paste the code into your coding window. I should say we are using R here mostly, and that is not a philosophical choice. We're very agnostic. If you prefer Python or Julia or whatever is your coding language, great. Our main message to you is to learn one coding language very well. Learning the next one is much easier, kind of like learning a foreign language. At least that's been my experience. And we find that most social scientists come from R, and most computer scientists come from Python or C or whatever you code in. And so we'll have to kind of be patient with each other to arrive at a compromise. But most of our examples are going to be in R today. OK. And again, just to those of you who are very new to this field, I want to encourage you to focus on learning how to learn. I'm about to throw a lot of information at you. And if you feel like you're getting behind, if you're unable to reproduce the steps in real time with me, kind of relieve yourself of that instinct to try to master a skill. I'm going to learn how to screen scrape. I'm going to learn how to work with an application programming interface. These are the two things we're about to talk about, right? Instead, try to learn how to learn. Try to focus on identifying the resources you would need to do these things. Because as we'll see, very often there's no single solution to extract digital trace data. And we have to learn to be flexible and approach a problem from multiple directions. OK. So here's what I just said about following along. Here's the link if anybody didn't find it earlier. OK. So one more thing about the slides. These are, again, the aforementioned code chunks. So when we are coding together, up top, these are the instructions we're going to put into RStudio, which is the graphical user interface that we typically recommend to work with. And then here at the bottom, in this lower box, you'll see the output of those instructions that we put into RStudio. So this is what it's going to look like on the slides. And again, this is what it looks like in the annotated code. So here's a chunk of code where we're going to discuss topic modeling tomorrow. And you see some description of what the code is doing, the code itself, and then the output of the code. OK. So first, let's start with this question, what is screen scraping? And typically speaking, it means identifying a web page that you can legally scrape. I'm going to emphasize the legally. Second, we're going to download the source code of that page, usually something like HTML data or XML data. And these are just formats that allow a web browser to visualize a page to us. And then very often, we want to parse through that data and extract some kind of data of interest and create a data set. And usually, we want to do this in an iterative fashion. We want to visit a lot of websites and get a lot of information, right? And populate something like a spreadsheet or a data frame. So the first question to ask, and this has already come up in our discussion of ethics yesterday, is screen scraping legal? I'm going to give you a bit of a cop-out. I'm not a lawyer, so I can't give you legal advice, but I can tell you some best practices. The first is to first visit the terms of service of a page that you might wish to scrape. And there, very often, you will see something called the robots.txt policy, TXT, which very often specifies the manner in which you are allowed to engage with the site in an automated fashion through a computer program. And many people are very discouraged to see that it is often the case that the site prohibits screen scraping. And we're going to move relatively quickly through screen scraping because for a variety of reasons, scrapable websites are becoming fewer. And websites that are still scrapable are becoming more difficult to scrape. And so typically, many people interested in working with digital trace data will want to use application programming interfaces, which are essentially pipelines for data transfer on the internet where we can make custom requests for large data tables rather than doing screen scraping. But almost everyone who works in digital trace data encounters a situation where they want to scrape a web page at one time or another. And so we'll work through a few different ways to do it. But first, the very first step is to establish whether screen scraping that page is legal. The terms of service are a good point to start with. And of course, contacting the owner of the web page is probably the ultimate way to determine whether you can legally scrape the page. And I want to point out again, this has changed, right? There was a moment in the history of the internet that I like to call the wild, wild west. People were really scraping everything and anything. Especially younger scholars were amassing large amounts of data. Many of those same scholars received a cease and desist letter from the owner of the site. And I'd like you all, especially younger scholars, to imagine the situation where you've scraped a bunch of data, and then several years from now you receive such a letter that effectively tells you can't publish your dissertation research, or that paper that was supposed to get you tenure if you're an assistant professor or a postdoc, right? So it's really important to understand these rules. And I think we have a question from the live stream.
Web scraping in R. Elliot from NYU wants to know if you can spend just a little time discussing the pros and cons of R and Python, especially the different packages that exist in each for things like screen scraping, topic modeling, natural language processing.
Sure, so we could spend all day on this topic, I'm sure, especially with this crowd. My general reaction is, again, learn one, right? I'm very agnostic about which package is best. They both have various advantages. I think historically speaking, it was easier to work with digital trace data and do text analysis in Python. That gap has closed substantially thanks to the work of a lot of developers in the tidyverse, which is a family of R packages. And we'll talk about some of those packages tomorrow. We'll talk about some of those packages today. One of the main reasons that I think R has advantages for computational social scientists is that it provides really easy access to the state-of-the-art in statistics. And typically, we want to move quickly from collecting digital trace data to analyzing it. And though Python has made amazing strides in pandas and elsewhere to develop that infrastructure, I think the fact that most faculty in statistics still code in R is a strong case for using R. But again, we could talk about this all day. Feel free to have a lively debate on Slack, but just in the interest of time, I think I'd like to keep us going. Okay, any other questions? No, okay. So another warning. So often screen scraping is illegal. Screen scraping is also very often frustrating. Why? Because this data is urinal-like, right? It was not made for you, the researcher, to easily get your data. It was made to help a web browser visualize a web page. And so that nugget of information that you want is hidden deep within some code that allows a computer to visualize the page. And that means that we have a kind of cat and mouse game to try to find it. And typically, we have to use a few different approaches and a lot of trial and error to figure out where the information lives. It's easy to download the web page, but navigating the web page and finding the piece of information we want is the frustrating part. So we'll begin simply by reading a web page into R. We're going to use a package called rvest. This is one of the aforementioned packages from the tidyverse. For those of you who are in the Python language, this is very similar and borrows heavily from the beautiful soup package. I don't know the etymology of that name. And that's a very popular package for a module for web scraping in Python. And so as we have to do with any R package that's not part of base R, we're going to begin by installing the package here and then loading the package into our session of RStudio. And we're going to begin by scraping a very simple web page from Wikipedia. So you can open it here in the slides, or it's also linked in the Markdown file. And what you'll see is this is some data on the ranking of health systems in a number of different countries. And this is a bit of a silly example because if we wanted to get these data, we would likely just come to this page and say highlight this table and then control copy and paste it into a spreadsheet or something like that. But let's say we wanted to do it for a lot of different web pages that had a similar structure. Well, the way we would want to do that is to begin by reading the HTML into R. So this is what the web page looks like to us, right? It has font and visuals and hyperlinks. And notice that it also has a layout and architecture and aesthetics, right? This font is larger. It's always at the top. This font is this table we all know from browsing Wikipedia gives us the kind of the table of contents, right? And to our web browser, all of these things are the result of a set of instructions, right? There are parts of HTML code that tell the web browser, put this at the top, put it in this font, and make it larger text, for example. And that's typically the type of stuff that we don't want to scrape when we scrape a web page. So what does that stuff look like? So I just showed you what it looks like to a human. This is what it looks like to a computer, right? Just nasty, ugly HTML, right? And here you can actually see the data we want is actually right in here, or some of it, the names of the countries if you zoom in on your own screens. But the rest of that data is hidden somewhere in this HTML. So we have to do quite a lot of legwork to find out how to get from this messy chunk of text to that neat table. So the way we're going to do that, the rvest package has a read_HTML function. And we can pass the hyperlink or the URL to that function. And we will create here an object in R called Wikipedia page. And if we browse that, we see it's a mess, right? It's not at all what we want. And that's because it's part of this HTML file. And HTML has a structure that looks something like this. It has a head and a body. It has a tree-like structure. And typically when we're parsing HTML, we're trying to learn how to tell our computer program how to navigate this tree-like structure and find the piece of information we want. So how to tell it to, usually the data we want is going to be in the body of the text. The head typically refers to the aesthetics. And so then, but even in here, and this is a very simple HTML page, our data might live down here. And so typically what we do is in a step-by-step process try to identify some codes that help us to identify which branch the information we want is on, and then write some code to go pull out that information. Okay. So a nice way to do that, if you use Chrome, is to go to your View menu. And if you come down to the Developer dropdown, you'll see something called Developer Tools. If you want, incidentally, if you want to see the source of the page that I just showed you, you could go to View Source, and then your Chrome browser will show the source. But if you come to Developer Tools here, this pane here will open up. And what you're seeing here is the HTML that we were just looking at alongside the page itself. And what's nice about this tool is that we can click and interact with the page here and learn which section of the HTML that data lives in. And the way we do that is to right-click near the data we want. In this case, we might click somewhere in our table here that we're trying to scrape. And if we right-click, we can select Inspect. And when we select Inspect, the associated part of the HTML code will be highlighted here. And we can then come over to that part and discover exactly where in our HTML tree our data live. And if we find that part, we can then right-click again, and we can find something called the XPath, which is essentially a set of instructions that is going to allow us to parse our HTML. It's going to tell us exactly where our data live. OK, I know I'm moving fast. Again, if you're trying to follow along in real time, you might want to step back and relieve yourself of that duty. Know that all the notes and explanations of each step are in that annotated code file that is linked on our webpage. OK, so now, once we've got that XPath, we're going to use another function called HTML node. And what that function does is parse the HTML to the node, to the part of that tree that I just showed you, where our data is living. And the HTML node function requires several arguments. First, it needs the name of the HTML we're trying to parse. Here, that's Wikipedia page. And then it needs an XPath argument. So that's that chunk of code that we just got by right-clicking on the HTML after having selected it using the Inspect option from the developer tools. And when we pass that and then browse it, so we're using the head command in R here, which simply visualizes the first 10 lines of an object, we see we're still not where we want, right? We still don't have that neat table. And so we need to use another function, because we've got down to the branch, but within the branch there's still a bunch of stuff. And what we want is this table. And so here, if we apply the HTML table function, once we're on the right node, it's going to pull out all of the table-style objects from that node. And here, I've defined that as a new object called health rankings using my assignment operator here. And then we're simply browsing that object. And we see that we've got still not super neat and tidy data frame, but we've got a list of countries. And we are getting much closer to the data that we actually intended to scrape. So we could then go on to transform that object into a data frame or export it as a CSV or whatever we want to do using, say, the write CSV function or, say, putting it into a data table. Okay. So, OK, very often this XPath does not work, or it works after much interaction with the page. Remember, this tricky part is interacting with the web page in order to learn which part of the HTML you need to work with to find the data. And so it's very often useful to take another path, something called the CSS selector. And we're going to use that to work with a more complicated page. This is the home page of Duke University. And as you'll see, unlike our Wikipedia page, it's a bit of a fancier page. We're pretty fancy here at Duke, right? We've got some interactive features, some JavaScript, which is like allowing different images to come up, and we can click on them, and those are redirecting us. We've got some news, a news section here that is updated each day. A lot of exciting news here at Duke. And so we face a greater challenge, right? Why? Because the source code of this page is about 20 times longer than it is for that Wikipedia page. And if you try to use the XPath to find this data, you may find it doesn't work. And so in this case, we can use a Chrome plugin called Selector Gadget. And what this tool does is much like the developer tools, it allows us to interact with a web page in order to extract. Actually, you can get the XPath using this tool as well. We can also get another chunk of code that's useful for parsing HTML called the CSS selector. And so the way this works, once you've installed the plugin, which will take a few minutes, so if you're following along live, you might not be able to do this, you'll see a little microscope icon appear at the top of your web browser. Okay? Then you'll see this little tool appear at the bottom of your page. And this is the area where your CSS selector code will appear that we're then going to use to pass to one of our RVest package functions in order to parse out the information we want from this page. The way that the selector gadget works is we first click on the data that we want. So here we are clicking on the news section. That's what we're in this hypothetical example. We're very curious about what's going on at Duke. So we've selected that. And then once we do that, we see a lot of other stuff get highlighted in yellow. And we need to then click on the stuff we don't want that's in yellow in order to, and often this takes multiple trials, clicking on different parts of the page in order to reveal a CSS selector down here. I should say you'll get one immediately after you start clicking on these yellow things. The trick is finding the right one. And again, this can be a very time-intensive process and a very frustrating process. And again, combined with the legal restrictions, these logistical challenges of screen scraping make it quite frustrating. So here's an example of once we've identified the CSS selector, again, using the selector gadget, the process then is very similar. We would simply read in the web page using our read HTML function. Then we would use our HTML nodes function, and here we're passing, instead of the XPath, the CSS selector. And then we're creating another object called Duke events. And then last time we used the HTML table function to extract the table. This time we want the text. It's not in table format. And so we'll use the HTML text function. And then we are simply browsing the output here. And you'll see that we got what we want. We got the names of the events. Now, if you're following along live, you'll get different events because the web page has changed. But then you'll see all these funny characters here, right? These /n/t and so on and so forth. These are a kind of residual mess from our HTML, often called HTML tags, telling the browser in this case to start a new line and put a space in between the text, right? And so tomorrow we'll go over in some basic text analysis ways to clean up these type of HTML tags in our data, which very often we don't want, especially if we're going to run a text analysis. And we don't want, for example, /t to have a meaning. OK, so we have a few minutes left. I think we have about 5 minutes. And I want to go over one last tool to have in your toolkit for screen scraping. And then we'll move on to application programming interfaces after the break. And then we'll move on to building apps and bots to collect digital trace data. And this final tool is browser automation. Again, this is another way of interacting with a computer in an automated manner. And essentially what we're going to do is, instead of finding the page and reading it in and extracting the information, we're actually going to open a computer program called Selenium, which controls our entire computer, which is a bit scary. Just as a little bit of a warning, we do live in an open source world, and it's good practice to understand that the package has been produced by a reliable developer, and that's often difficult to do, but some good cues are the amount of community, the number of people who are involved in discussions, say on GitHub, about the maintenance of the package, and also the reputation of the developers. So you can look at reputation on GitHub in a number of ways. I think there was a question or a comment. You tried to start Selenium. Yes, yeah. So I'll get to that in just 1 second. One of the pleasures of browser automation is working with some very buggy software. Yeah. So long story short, there could be a Java issue. So very often you have to install an older version of Java on your computer to get browser automation to work. And just yesterday, Karsten and Frito discovered that there's a particular issue with the ROpenSci package that was in our code here. And this is a good teachable moment, right? In this landscape, the ground is always moving, right? And this is why I'm so adamant that you need to learn how to learn instead of trying to think of, now I've acquired the skill of screen scraping and now I'm going to move on, right? You need to know what happens when the package breaks. In this case, the code I think I've got here isn't working, right? And we Googled the error message. We were redirected to a GitHub page. We discovered an issue, which is a way of tracking what's going on with a package. And lo and behold, 2 or 3 comments in, a solution. And so if you want to follow along with this code, you'd have to do that, unfortunately, depending on, again, what the issue is. It could also be a Java issue. Anything to add to that, Frito or Karsten? No? OK, great. OK. So what we're doing, and by the way, there's a tutorial linked right here that helps you install our Selenium across a number of different operating systems. OK, so what we do essentially once we've got Selenium running is we are creating a kind of object that allows us to control, in this case, our browser. That's what these 2 functions are doing. And once we do that, we can then control the object, which is called remdr for remote drive, right? And we can say navigate to this link. And if we have Selenium installed, and if we run this link, a Chrome browser will open, and it will open www.duke.edu. One of the powerful things of browser automation is we can not only give instructions to, say, open a web page, but we can also give instructions about how the program should interact with that web page. So in this case, we can find the search box. And in this hypothetical example, we are, let's say we're trying to search for news about data science at Duke. And so here we would use the CSS selector to find the search box using the steps I showed you earlier to identify how to tell Selenium where to click. It's actually literally clicking on the page in order to enter a search. And that's what this set of instructions is doing here. And then we can actually tell it which keys to type. We can tell it to type in a search term. We can tell it to press enter. We can tell it to press space or tab or whatever. And these can be advantageous if you're working with a web page that has a lot of interactive JavaScript or where you need to go back and forth to interface with the page. Now, very often, these type of pages that require that level of interaction, you are not allowed to scrape. So be aware of that. So for example, something like Google, where you might be able to use browser automation to collect a lot of data, but Google expressly prevents you from doing that for the vast majority of its sites, right? And perhaps more importantly, Google provides alternatives, which we're about to talk about, called application programming interfaces, which are not only legal, but much easier to work with and will prepare your data in a neater format. You might not be able to get the data you want, but again, that might be because it's illegal to get the data you want. So proceed with caution with browser automation. It is just another tool to have in your tool belt, but it does test the limits of the robots.txt policy because it begs the question of what is a computer program and what is a person. And Probably the lawyers would argue that this is a computer program, and I think I would agree with them in many cases. Okay, so I've introduced 3 tools for screen scraping in this short lecture. In each case, we were just scraping one page to get one piece of information. But again, very often with screen scraping, you're wanting to iterate across a lot of different websites or a lot of different objects. And so to do this, we very often need to write a loop. And if you've done our data camp exercises, you'll have some familiarity with code like this, which is telling you how you might take a list of websites and create a blank container or a place to store the data that you are going to scrape iteratively from them, and then a set of instructions placing the code from earlier within our loop with a set of instructions about what to change each time through the loop. This code, by the way, will not work. And there's an intentional reason for that, to explain to you that it's very often the case that unless you are going to scrape the same web page and the same web page that has a very similar structure to another web page, you're going to have to write custom code for each page that you're going to scrape. And so another major disincentive for screen scraping is that, let's say we wanted to scrape all the pages of major US or international universities to get information about computational social science. Well, we'd be dealing with dozens or hundreds or thousands of different types of web pages. And so we may very quickly find ourselves in the world where writing the code to scrape those pages takes longer than going to those pages manually and scraping that pages. And that's yet another reason why very often we don't want to use screen scraping. But let me conclude with a brief discussion of good times or ideal cases for screen scraping. These are very often more simple websites. So many government websites do not prohibit screen scraping. Some administrative data live on non-protected websites. And particularly if these are older websites that have the same structure, and if there's a particular pattern in the URL that allows you to say, look at the top of the URL in your browser and say, oh, it looks like the date is changing at the end of the URL. And each time I change the date, then I get a different list of information. If it's something as simple as that, then you can simply write a loop that then says, change the date by using some type of concatenate function. In R, that would be the paste function, and change the URL that you are passing to our read HTML function that I just described in an iterative fashion. OK, so that's it for screen scraping. If folks on the live stream have questions, I'm happy to answer them on Slack later today. And when we come back from our break, we'll be talking about application programming interfaces. Thank you.